All right, good morning, ladies and gentlemen, and welcome back, this time to the finals of the National Materials Competition 2024. We are honored to have our distinguished VIPs, juries, and presenters here today. Please ensure your cameras are working and you are muted as we prepare to begin the event. We would like to start our event with our national anthem, Negara Po. All right, thank you, everyone. So I would like to welcome you all once again to the finals of National Materials Lecture Competition 2024. My name is Isha, and I will be your MC for today. To start off, I would like to reintroduce you to the competition guidelines. The first being about the participation. The National MLC 2024 will be conducted in a live session. All competitors are required to attend and deliver their presentation through Zoom. The link has been provided by the host via email previously. Regarding the program schedule, competitors can refer to the tentative program for the presentation schedule. Please be present at all times during the competition to avoid any delay of the event. Presentation slides. Competitors are responsible for controlling their own presentation slides. However, in case of any technical difficulties, the host technical team will be available to assist in sharing the slides. Presentation time. Each competitor must deliver a 15-minute presentation in English on a topic related to materials or mineral science and engineering, followed by a 5-minute Q&A with the esteemed panel of judges. Presentation ethics. Competitors are expected to dress in a formal attire and have their video cameras turned on during their presentation. Cameras may be turned off when the competitor is not presenting. From 13 presentations during the semifinal, we have narrowed down to the top 5 presenters within the nation. We have an exciting lineup of presentations ahead, showcasing the brilliance of material science across Malaysia. All right. Allow me to introduce you to the esteemed juries who will be evaluating today's presentations. First up, we have Dr. Nisa Mazlan, who is the Associate Professor at the Department of Aerospace Engineering, University Putra Malaysia, UPM. She is the head of program of the Nanomaterials Processing and Technology Laboratory at the Institute of Nanoscience and Nanotechnology. She is also the core researcher at the Aerospace Malaysia Research Center at UPM. Next, we have our second judge, Senior Technologist Nur Hisham bin Yahya. He is involved in plant turnaround, project construction, and maintenance in contracting works in refineries and petrochemical plants in Malaysia. Involved in asbestos abatement services, TVET modules development and training, as well as consulting services in construction audits and failure incidents investigation. Currently, he is the IMM's Deputy President. Next, we have our third judge, Dr. Mariam Jamila binti Ghazali, who serves as a professor in the Department of Mechanical and Manufacturing Engineering in UKM. She is a visiting professor at Nagaoka University of Technology and Sophia University, Japan. She's also the Assistant Dean of Entrepreneurship and Chief Director of the journal Kejuruteraan UKM. She's also the co-founder of the Malaysian Tribology Society. Finally, we have technologist Kang Kim Ang. He specializes in corrosion control, cathodic protection, pipeline integrity, inspection using MTM, MTMG technology, and heavy-duty coatings across oil, gas, marine, petrochemical, construction, and industrial sectors. He is a registered professional technologist with MBOT and has over 7 years of lecturing experience in corrosion engineering industry. May I request all our respected juries to kindly turn on the camera so we can have a photo session with them. Want to join? All right, 1, 2, 3. One more time. 1, 2, 3. All right, thank you, everybody. Your speech. All right. All right. To kick things off some more, let's welcome the organizing chairperson of the National MLC 2024, Dr. Muhammad Khairi Faiz, for the welcoming speech and recital of dua.
Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. Dr. Abdul Hakim Muhammad Yusuf, the IMM MLC chairperson, honorable judges, esteemed finalists, and everyone who attend today's Materials Lecture Competition 2024 National Level Final Round. Hello everyone, on behalf of the organizing committee, I'm excited to welcome you to the final round of the Materials Lecture Competition 2024. It's wonderful to see all of you joining us online today to celebrate the incredible talent in materials science and engineering. To brief, this year we had 13 outstanding participants from various universities, and now we are down to our 5 exceptional finalists. Each of you brings unique insights that are sure to inspire and engage us all. I am especially thrilled to announce that the winner of today's competitions will have the honor of representing Malaysia at the Young Person World Lecture Competition 2024. This is an incredible opportunity, and we cannot wait to see who will take on this important role. A special thank you to the Institute of Materials Malaysia for providing cash prizes for all of our winners. Your support helps recognize the hard work and dedication of our participants. I also want to give a big shout out to my committees. Okay, thank you all for your incredible efforts in making this online event possible. Your dedication has been key to bringing us all together today. And to our finalists, I wish you the best of luck. Share your research with the passion and creativity that got you here. Your work is crucial for advancing our field, and we cannot wait to hear what you have to say. Finally, a heartfelt thank you to everyone tuning in today. Your support enriches this experience. Now, before I end my welcoming speech, let's join me for a short dua prayer for a meaningful event today. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Ya Allah, Ya Rahman, Ya Rahim, we thank you for this opportunity to gather and share knowledge. We ask for your blessing on this event. Grant our participants clarity of mind and a smooth tongue so they may present their work with confidence and passion. May their efforts lead to a fruitful discussion and inspire others in the field of material science and engineering. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم والحمد لله رب العالمين. With that, let's dive in and enjoy the competitions.
We were meant to have Prof. Hendrik's speech right about now. However, he sends his regards as he cannot currently attend and be here with us right now. So now we will move on to the next phase, which is the finalist introduction. So as you know, last 3 weeks ago, we decided on 5 top performers in the entire Malaysia, and today they are going to compete to represent Malaysia on an international level. So let's introduce our finalists without further ado. Each of them will present their cutting-edge research today, and I will call their names in the order of presentations. First, we have Natasya Salsabiila from University Tun Hussein on Malaysia. Next, we have Normaiza binti Nordin from University Malaysia Sabah. Third, we have Jerome Liew from University Malaya. Up fourth, we have Ainaa Amirah binti Marzuki alias Mahdi from University Technology Malaysia. And finally, we have Aslam Hadi bin Hamzah from University Technical Malaysia Melaka. Let's give them a round of applause. Now we would like to proceed with a group photo inclusive of all the participants and all the judges. So I would kindly request everybody to turn on their cameras so we can take a group photo to commemorate this event. All right, are we ready? Participants, are you all right? We see you all. All right, 1, 2, 3. One more time, 1, 2, 3. Smile, yeah. All right. And last one, 1, 2, 3. All right. All right, now we will just head towards our presentations. First up, as you all know, is Natasya Salsabiila from University Tun Hussein on Malaysia with her presentation on effect of amine and thiol as functional groups on gold nanobipyramids properties for glucose sensing. Natasya Salsabiila, are you here right now?
Yes, I'm here. Can you hear my voice?
I hear you.
Okay.
All right. Good luck.
Okay, I will.
You may not share your slides, yeah.
Okay, I will share my slide. Okay. Is my slide visible?
Yes, it is.
Okay. Are you familiar with this? Or even this? I'm sure that all of us like to consume them because they are very delicious and convenient. You can get them anytime and anywhere. If you see, people nowadays prefer to consume them rather than mineral water and lack of exercise. So this simple thing can give us a brief understanding of why diabetes is very popular and still become an issue for the next few years. Diabetes is very scary. It can cause so many deaths, with only 60% had a proper diagnosis. And this condition will worsen until at least 2045. Hence, the need for glucose sensing method has gained much attention and improvement over the years. Let's start by looking at our current method to measure glucose level. Most of you are familiar with glucose meters, right? It requires finger prick, which is very painful and invasive. Another method is through urine test, but it requires long-time detection and medical expert to analyze the result. Not very convenient, right? So can we find a better, a more user-friendly solution? This is where plasmonic sensor come in. The sensor can be performed in non-invasive way, fast detection, and of course, can be performed by everyone without an expert needed. However, the challenge is to do glucose sensing using plasmonic sensor needs to be improved in the selectivity and stability aspect. But wait, how can we develop a plasmonic sensor with a dose of advantage, with improved selectivity and stability aspect as well? Okay, one of way to achieve that is through sensing material modification. So here I am, I'm Natasya, and today's lecture will discuss about the modification of gold nanobipyramids using amine and thiol groups as sensing material for glucose sensing application. Basically, there are a lot of materials on this earth, right? Both in the bulk and in the nanoscale. The nanoscale material, well known as nanoparticle. For your information, nanoparticle itself has increased surface area that is very suitable for the sensing application. But why did we focus on metal nanoparticle? So besides high surface area, metal nanoparticles are very reactive to the living cell. So it's very promising feature to be applied in the biosensing application field, and it can be used to detect very low concentrations of target analyte. There are a lot of types of metal nanoparticles, but gold become the popular one because it's very easy to modify with other molecules, so it can be used to detect various things. And then we came up to the next question. What type of gold nanoparticle that can be used? Let me introduce you to our key players, which is gold nanobipyramids or GNBPS. This material has a higher sensitivity response compared to other form and the facile functionalization process, so it can be used to detect certain molecules. In this case, we want to use gold nanobipyramids or GNBPS to detect glucose molecules. So the functional group used are amine and thiol because they can construct a strong chemical bond with glucose molecules on the gold nanobipyramid surface. Then, how can we produce gold nanobipyramids or GNBPS? The most popular method to synthesize gold nanobipyramids is through seed-mediated growth method or SMGM, which divided into seeding and growth process. In seeding, we produce gold nanoparticle as a seed, then the seed will be grown into the bipyramid shape in the growth step. After that, we functionalize gold nanobipyramids using amine and thiol groups for 0.5 until 72 hours to modify the surface of gold nanobipyramids so they can properly bond with glucose molecules. The interaction between amine and glucose molecule is known as imine bond, while thiol and glucose molecule is known as disulfide bond. Okay, we already know how to synthesize and then functionalize the surface of gold nanopyramids, and this is the result solution. And then in the synthesis, there is a mechanism of growth from seed. So increasing time leads to the decrease in the gold source, which affect to the production of truncated and gold nanopyramids, or GNBPS, cannot grow in the perfect shape. And then we have figure 2, shows a GNBPS, or amine functionalized GNBPS. Find a solution for 0.5 until 72 hours. We can see here that after 12 hours, the solution turned light yellow. Next, figure 3 shows T GNBPS, or thiol functionalized GNBPS. Find a solution for 0.5 until 72 hours. If we see here that after 12 hours, the solution turned darker. Now, we have the characterization result for pure GNBPS using UV-Vis, XRD, PSAM, and then we also have TM, zeta potential, and the last one is FTIR to confirm that gold nanopyramids, or GNBPS, have been successfully synthesized. Next, let's move on to the A-GNBPS, or amine functionalized GNBPS. This is the UVB spectrum of A-GNBPS. We can see here that in general, the spectrum shifted into the red region, indicates an increasing in the aspect ratio. So for your information, aspect ratio is the ratio between length and width of gold nanopyramids. And the highest absorbance value is obtained at 3 hours, with over 12 hours, there is no peak anymore in the absorbance spectrum, indicates that there is no nanoparticle remaining in our solution as a side effect of our functionalization using amine groups. Then we have XRD here. So this is the XRD pattern for A-GNBPS. We can see here that there is additional peaks, consists of amine molecules such as Si, N, H, and O, with the highest additional peak is obtained at 3 hours, indicates that the highest interaction between amine groups and the surface of gold nanopyramids occurs at 3 hours. Next, PSAM. So this is the PSAM pictures of A-GNBPS. Based on these results, the highest surface density is obtained at 3 hours with value of over 59%. Next, we have TM here. So based on these results, the tip and slope angles of A-GNBPS is 1.01 times higher than pure GNBPS, indicates an initiation of surface scraping phenomenon conducted by amine groups that allows for the morphological change. With zeta potential value measured at 2.1 millivolts, which is increased from pure GNBPS, and the last one is FTIR. We obtain that the utilization of amine groups to modify the surface of gold nanopyramids can influence for the wave number shift. Next, let's move on to the T-GNBPS, or thiol functionalized GNBPS. This is the UV-Vis result for T-GNBPS. We can see here that in general, the spectrum shifted into the blue region, indicates a decrease in the aspect ratio, so a bit differ from A-GNBPS before, right? With the highest absorbance value is obtained at 3 hours as well, with over 12 hours, the spectrum turned broader, indicates that the shape of nanoparticle is not typically bipyramid. Next, we have XRD. So this is the XRD pattern for T-GNBPS. We didn't see any additional peak here as GNBPS before, A-GNBPS before, right? Indicates the purity of nanoparticle itself. But if we clearly see, the usage of thiol groups can influence for the growth of 111 and 200 plant. Next, PSAM. So this is the PSAM pictures of T-GNBPS. And based on this result, the highest surface density is obtained at 3 hours with value of over 75%. Then we also have Tm here. Based on this result, we didn't see any morphological change, right? As AGMBPS before, with zeta potential value measured at minus 0.1 millivolt, which is decreased from pure GMBPS, and the last one is from FTIR. We also obtained that the usage of tile groups to functionalize the surface of gold nanopyramids can influence for the wave number shift as well. Okay, we already know how to synthesize and functionalize the surface of gold nanopyramids, and we also know about the properties change after the functionalization process. And here is the mechanism for functionalization process itself. So, based on the characterization results, it is obtained that amine groups influence for the morphological change, while thiol influence for the nanoparticle agglomeration. And this phenomenon also corresponds with the general understanding of zeta potential value, where positive charge of amine influence for the nanoparticle agglomeration inhibition and vice versa for negative charge of thiol. Okay, we came up to the next stage. How can we develop a plasmonic sensor to detect glucose molecules? So here is the sensor setup used, which consists of light source, fiber optic, chamber, spectrometer, and the last one is computer equipped with a software analyzer. So gold nanopyramids as sensing material and glucose as target to analyze will be placed in the transparent cuvette with ratio 5:1 and then put in the chamber. Then light from the light source will be exposed to the chamber through the fiber optic. So when gold nanopyramids detect glucose, it can cause a spectrum shift towards the localized surface plasmon resonance or LSPR spectrum. Then the spectrum will be recorded by the spectrometer, and the last one is visualized using computer software. For your information, localized surface plasmon resonance is the optical phenomenon conducted by all of metal nanoparticles when they are irradiated in lines with specific wavelength and is very sensitive to the surrounding medium change. Then, we want to know about how gold nanopyramids perform when detecting glucose molecules. So we proceed pure GMBPS, A GMBPS, and the last one, we also have T GMBPS for plasmonic response mechanism testing. And based on this test, it is obtained that pure GMBPS, A GMBPS, and T GMBPS can detect different medium denoted by intensity change and wavelength shift. Of course, we want to know about what is the optimum time to functionalize the surface of gold nanopyramids so we can get the best signal response for our plasmonic sensor application. Based on this result, 3 hours of A GMBPS and T GMBPS has the strongest signal response compared to other, denoted by the highest intensity value. These conditions also corresponds with the characterization result, where 3 hours has the highest absolute value and the highest surface density value. Okay, ladies and gentlemen, we also have the selectivity performance of the plasmonic sensor when detecting glucose molecules using pure GMBPS, A GMBPS, and the last one is T GMBPS as sensing material. And we have there that basically A GMBPS and T GMBPS perform a higher selectivity response compared to pure GMBPS, with A GMBPS has the best selectivity response. After that, we also have the stability performance of the plasmonic sensor when detecting glucose molecules using pure GMBPS, A GMBPS, and the last one is T GMBPS as sensing material. We can see here that basically A GMBPS and T GMBPS also perform a better stability response compared to pure GMBPS through a lower error value, with T GMBPS has the best stability response. Okay, now I will summarize the whole discussion. So overall, gold nanopyramids have been successfully synthesized and then functionalized using amine and thiol groups, where amine influence for the morphological change, while thiol allows for the nanoparticle agglomeration. And when we proceed into the selectivity and stability testing, it is proven that the utilization of amine and thiol groups to modify our sensing material can improve the selectivity and stability performance of the plasmonic sensor when detecting glucose molecules. But wait, we are not done yet. So there is still a room for improvements. For example, about the development of the portable gadget so we can use it into the real sample testing in the field, and also the integration with AI or IoT system. And that's all from me. Thank you for your attention.
Okay, thank you, Natasya Salsabiila. So can you hear me?
Yeah.
Yeah, okay, all right. So thank you for your presentation, very insightful. Lots of technical things, huh? Okay. So I would like to call Professor Dr. Mariam first to give a question to Natasha. Please unmute.
Okay, so sorry about that. My apologies. Okay, thank you, Dr. Nisa. And I would like to take this opportunity to say congratulations, Natasha, to come up this far. Right. Okay, before I ask you a question, I just want to give a bit of I would say not comments, just take it as a suggestion, yeah. I think the title that you presented to us just now is a little bit too academic, and it's and formal for a general audience, yeah. And throughout your presentation, I think I see that the content is very rich in information, very informative, but I think it might be very difficult for non-experts to understand. Okay, it is lacks clarity for the general public. Right. Okay. My question here. I like the way you started with the current problems. You claim that the existing or the current method is painful and a bit of time consuming, right? So how does your GPNPs method addresses these shortcomings?
Okay.
Or surpass this limitation? Yes.
Okay, thank you for the question. So I would say that the question is about how we can address the issue regarding to the conventional method, right? So the conventional method, when you use glucose meters, it's invasive and painful. So by using plasmonic sensor, we offer additional method, which is we prefer use another sample such as sweat, saliva, and urine. But we prefer to use saliva instead of any other samples. And the second one, for urine testing, it requires long-time detection and performed by expert. So for your information, a plasmonic sensor can create one graph or one result in only 1 second. So you can imagine when the diabetic patient use the plasmonic sensor for 5 minutes non-stop, it will create so many data, right? And the data can be monitored and managed in the real time. And the third one is about can be performed by everyone without an expert needed. So we will include the sensing material or golden obey permits into the one package of plasmonic sensor version of portable gadget. So when diabetic patient want to check their blood glucose level, they just put the sensing material along with the sample testing such as saliva, and then they just turn on the light source. After that, the result will be created. So as simple as that, and can be performed by everyone.
Okay, thank you. I think you should highlight that. I think you should highlight that in the presentation next time. Okay, thank you very much.
Okay, thank you, Professor Mariam. Okay, next, technologies, Kang. So please give one question to Natasha.
Yeah, interesting. Try to catch a few important points there. Especially think of the pain for people who would like to test the samples from the body. I always see the people have like doing something on the fingernails, and we hate to have that during the blood test. Now, I'm just curious, just very non-technical question. In your presentation, it looks like there was a lot of the dealing with the functionalization time. Could you explain why is it important to find the right functionalization time when modifying these nanoparticles for your glucose sensing? Why is it that time is important?
Can you hear my voice?
Yep.
Okay, thank you for your question. So we should consider about what is the optimum time, right, to functionalize the surface of polynomial. Why? Because first, when we use amine groups to functionalize the surface of polynomial of a period, it can cause a morphological change, will cause a decrease in the sensitivity aspect. Because the reason why I choose polynomial because polynomial has a higher sensitivity response compared to other forms such as rod, rice, spherical, and so on. So when the morphological tend to change, of course, it will cause a decrease in the sensitivity performance. But in other side, when we functionalize in under time, under period, it can cause the decreasing in the sensitivity response as well, because the amine groups cannot properly attach in the surface of polynomial pyramids. And based on our result, the optimum time is 3 hours. And when we talk about tile, it's a bit similar with tile. So when we functionalize the surface of polynomial pyramids using tile groups, it can make the agglomeration phenomenon. They also can decrease the sensitivity response. But when we functionalize using tile groups in under periods, it also cannot increase the sensitivity because the tile groups cannot properly attach in the surface of polynomial pyramids. So what I would like to say is about optimum time is very important, because both over and under, it can cause a decrease in the sensitivity performance. That's all.
Okay, all right. So one last question from Engineer Hisham Yahya. So please have one last question to Natasha.
Assalamualaikum, Natasha. Okay, quite interesting research that you are currently doing. Okay, my question actually with respect to the commercial values of it. Can you actually explain to us on what would be the accuracy level expected from this new Gen BPs with amine and thiol, and what will be the sensitivity with regards to storage and handling?
Okay. Thank you for your question. So if we compare to the commercialized one, actually I accept that our current research in the fourth level, which is if we see from the RTL, the readiness technology level, which is in the fourth level, which is just laboratory scale level. So if we want to proceed until commercialization, of course we should develop this type of sensor into the portable gadgets. And when we successful to develop this type of sensor into the portable one, of course it can be used by everyone, because we of course we will include the sensing material as well into the thin film fashion, so they can use it. And we also can include how to SOP, something like that, so everyone can make it without any expert needed. And about the sensitivity, our current limit of detection is about 1 micromolar. So with this kind of value, I'm sure that the sensitivity of the sensor also can be very challenged into the existing glucose meters.
Okay. So, did she answer your question, Engineer Hisham?
The aspect of storage and handling. So can you actually, because once you're going to be commercialized, you'll be actually placed in pharmacies and many other places. So we just want to see the aspect of storage handling.
Okay, thank you for the question. So about the storage, since this stage in the laboratory scale, we use solution form. So when we talk about storage, it not that kind of good, because the solution just only can once time. And when we proceed into the thin film fraction, that kind of thin film can be stored in the long time. And for the stability, it's 10 to 1 week and over. So we want to proceed into the thin film so we can storage into the longer time.
Okay, all right. So I believe there is lots of studies need to be done, yeah, before the commercialization process. Okay, so thank you, Natasya Salsabiila. So we can proceed to the next participant, Normaiza binti Nordin.
All right. Thank you,
Morning,
judges,
Natasya.
and thank you, Natasya Salsabiila. I believe now Normaiza is already here, right? Okay, so currently we will have Normaiza binti Nordin from University Malaysia Sabah with her presentation on Nafion membrane in microbial fuel cell properties and proton transfer mechanism. So let's welcome her. I will stop sharing my screen now. Yes, we see your slides. You may begin. Oh, you have to unmute yourself first, sorry. She's not okay. Normaiza, are you ready?
Yeah, I'm just
All
need
right.
to, okay. Okay. Bismillahirrahmanirrahim. Assalamualaikum and good morning, everyone. It's great to see you again for today's final. For those meeting me for the first time, especially our respected judges, my name is Normaiza binti Nordin. I am a master student from University of Malaysia Sabah, and I'm doing a research about microbial fuel cell for bioelectricity generation. So before we start today's lecture, let us talk about electricity just a little bit. I believe all of you can agree if I said all of us are highly dependent on electricity in our daily basis, right? So on the slide here, we can see the pie chart that shows the source of electricity in Malaysia. It was reported that more than 80% of our source of electricity now derived from fossil fuel, and only 17.2% is from renewable energy, which mainly hydropower, and less than 1% is from oil. Well, I'm not denying that fossil fuel is an excellent source of electricity, but the downside of fossil fuel is it is a non-renewable energy, which means it can get depleted over time and potentially jeopardizing our energy security if not tackled properly. Plus, it is not an environmentally friendly option. But the good news is Malaysia is now shifting towards a low carbon energy. They are now focusing on other alternatives that are environmentally friendly and are renewable as well. So as an effort, they have introduced the National Energy Transition Roadmap with the goal of moving towards a low carbon nation. And as a groundwork towards this transition, they have also updated the energy policy and introduced the National Energy Policy 2022 to 2040. Now, let me give you an example of bioenergy technology that are still in development now, which is microbial fuel cell. And yes, that is the topic of my research. And the amount of research and the increment in the amount of research on microbial fuel cell actually signifies the relevance for us to study this technology. So for today's lecture, instead of talking about the whole part of the MFC, I would like to narrow down the scope and bring your attention to only one part of the system, which is the Nafion membrane in the microbial fuel cell. And we are going to take a look on the properties and also the proton transfer mechanism. But before that, let me give you an idea of how I'm going to carry out today's lecture. First thing first, of course, I will introduce to you what microbial fuel cell is, or in short, I will call it MFC. So I will show you the application, the configuration, the working principle, and I will show you where we can find the Nafion membrane inside the MFC, okay? And then we will continue with the Nephron membrane structure, its properties, and also the proton transfer mechanism. And lastly, some potential future research on membrane. Okay, to begin with, microbial fuel cell is a bioelectrochemical system that utilizes microorganisms as biocatalysts to convert chemical energy into electrical energy. Okay, I don't want to confuse you with this definition. So I will give you an example of the technology that we already have out there in the market that is almost similar with microbial fuel cell, which is battery. Yes, battery. So the difference between battery and microbial fuel cell is battery use chemical electrolyte, which is not renewable. But for microbial fuel cell, instead of using this chemical electrolyte, they use microorganism and also substrate that we can actually obtain around us. Okay, so just to let you know, not all microorganisms have the ability to produce electricity, but microbes that have this ability is called exoelectrogens. So these exoelectrogens can produce electron and then transfer this electron outside their cell to a conductive metal, which we call electrode, with help of a mechanism that we call as extracellular electron transfer mechanism. Okay, this is a topic for another time. For substrate, it can be any organic waste. It can be sludge, wastewater, domestic or industrial waste, or even biomasses. Okay, in terms of application, besides for bioelectricity production, this technology, MFC, can also be used for simultaneous wastewater treatment, heavy metal recovery, detection and bioremediation of toxic contaminant, and sensors. Okay, now let's continue with the configuration. I believe all of you know how does a battery looks like, right? So a battery comes in various sizes, various configurations, same goes to MFC. MFC also comes in various configurations, but on the slide here, we can see the two examples of the basic MFC configuration, which is the single chamber MFC and dual chamber MFC. Again, similar with battery, MFC also have the negative and positive terminal. We called it negative terminal is the anode and the positive terminal is the cathode electrode. Okay, so the difference between this single chamber and dual chamber MFC is single chamber MFC does not have a defined anode and cathode chamber, which means the anode and cathode electrode are placed in one single chamber, one single compartment, okay? But for dual chamber MFC, they have a defined anode and cathode chamber that was separated by a proton exchange membrane, or in short, we call it PEM. And most commonly used PEM is Nephron membrane. And this is the part that we are going to discuss in today's lecture, okay? So to give you a clearer picture on how a dual chamber MFC can exist in real life, I would like to share with you the setup that we have used in our research. So this is the schematic diagram of our dual chamber MFC. These are the graphite rod cathode electrode and the stainless steel mesh anode electrode we use in our study. This is the Nephron membrane. This is the Nephron membrane that we use to separate this anode and cathode chamber in our study. And this is the complete setup where we have the peristaltic pump and magnetic stirrer there to provide the substrate circulation inside the MFC. And on top of that, we have the dual chamber MFC, which was connected to a multimeter and a laptop for us to record the electrical current output. Okay, now you already know about the configuration and the application. Let's continue with the working principle. I believe you must be wondering, maybe a little bit wondering on how the interaction between the bacteria and also the substrate able to produce electricity, right? So what happened during the operation is oxidation reaction and reduction reaction take place in the anode and cathode chamber. So in anode chamber, sorry, in anode chamber, the bacteria will consume the substrate and oxidize it. The keyword is oxidize it, producing three major products, which are carbon dioxide, electron, and also proton. This electron was first transferred from the bacterial cell to the electrode, and then it will continue its journey from the anode electrode to the cathode electrode through an external wire, okay? Proton, on the other hand, will also move from anode to cathode, but by passing through the proton exchange membrane, or in our cases, we use the Nephron membrane. So the Nephron membrane here is used firstly, to separate the anode and cathode chamber. Secondly, to facilitate the proton transfer activity. Thirdly, to block any huge molecules and anionic species from entering the anode and reacting to the anode electrode. Okay. In cathode chamber, that is what happened in anode. Now let's move to cathode chamber. In cathode chamber, reduction reaction takes place. So the oxygen that are present in the cathode chamber will pull the proton and also electron, reacting to it, producing water. Okay, so the overall redox reaction here, from the production of electron and proton to the transfer of electron and proton from anode to cathode, consequently produce electricity. And the performance of this MFC in producing electricity can be affected by several factors. And one of it is the efficiency of the proton transfer passing through the Nepean membrane. Okay. And that is actually one of the parameters that we have tested in our study. On the slide here, we can see the result that we have obtained, the current output comparison between MFC with untreated Nepean membrane and also treated Nepean membrane. Just to be clear, the Nepean membrane, we treat the Nepean membrane by boiling it in distilled water and then 3% hydrogen peroxide and 0.5 molar sulfuric acid. So, coming back to the result, this result here showed that when the MFC was equipped with treated Nepean membrane, it's able to record electrical current output above 6 microamp. Meanwhile, for MFC with untreated Nepean membrane, the electrical current output only able to record current below 4 microamp, not even reaching 4. Okay. So this is because why the treated Nepean membrane have higher electrical current output is because when we treat the Nepean membrane, it enhances the proton conductivity, which consequently increase the electrical current output. So to understand further on the factors that affect the efficiency of this proton transfer, we have to understand on the properties and also the mechanism, the proton transfer mechanism within this Nepean membrane. Okay. And to do that, we have to take a look on the structure. So Nepean membrane is a sulfonated tetrafluoroethylene copolymer, which consists of hydrophobic fluorocarbon backbone attached with hydrophilic sulfonate group. So this structure is responsible in determining the properties of this membrane. And due to the unique hydrophilic and hydrophobic structure, the membrane selectively permits certain ions such as proton, but block huge molecules and anionic species such as oxygen from passing through the membrane. That is the first properties. Secondly, the sulfonate groups. The presence of sulfonate groups here facilitate high ion exchange capacity, including the proton transfer mechanism. But since it is hydrophilic, so this activity is highly dependent on the hydration level. Okay, so to understand more on the relation between the hydration level and also the proton transfer, let us take a look at the Grott's mechanism. So this Grott's mechanism is the one that facilitates the proton transfer from anode to cathode. Okay, so this is actually the structure of the sulfonate groups in Nepean membrane. This is when these sulfonate groups get in contact with water, they will form a hydration layer, okay? And within this hydration layer, there is a formation and breaking of hydrogen bond. And this can occur when the proton encounter the sulfonate groups, forming temporary hydrogen bond. So for this proton to move from one sulfonate groups to another sulfonate groups, it have to form another hydrogen bond with nearby water molecules. So this is when the water become important in the proton transfer. For this proton to move from anode to cathode, for this proton to move from one sulfonate group to another sulfonate groups, they have to hop first from the sulfonate groups, hopping to water molecules, back to sulfonate groups, back to water molecules until it reach the cathode chamber. Okay. And this effectiveness of the Grott's mechanism, the proton transfer mechanism, actually can be affected by several factors also, which are hydration level, temperature, mechanical stability and durability, membrane thickness, pH level, biofouling, ion exchange capacity, and contaminant and impurities. Now, let us go back, rewind back the result that we have obtained. Let me remind you that in our MFC with treated nephron membrane, it able to reach higher electrical current output. That is because when we subject the nephron membrane with acid treatment, it will form new or larger hydrophilic domains that increase the hydration level of the membrane, which facilitate more proton transfer within the membrane, and then consequently increase the electrical current output. Okay, so the reason why I decided to share with you about nephron membrane today is because even though the amount of research on MFC is increasing, but it's slowing down now due to high cost and recycling issue of the membrane. So one way to overcome one way to overcome this issue is by discovering other alternative for nephron membrane, such as the fabrication of earthen membrane. So this research have been carried out previously actually by Pranab and Kaustuba, where they fabricate the earthen membrane by using combination of clay, bentonite, fly ash, and other material. And based on their result, it showed that the cost in fabricating the earthen membrane only cost them around 73 ringgit per square feet, which is cheaper, way more cheaper compared to the nephron membrane that cost them 4,000 ringgit per square feet. Okay, so for potential future research, beside discovering other potential material, we also have to focus on improving the effectiveness of the alternative membrane as well. So in conclusion, by understanding the properties, the mechanism, the advantages and disadvantages of nephron membrane, it actually can guide us in developing alternative membranes that are cheaper and also efficient. So this can help advance the development of MFC technology. So before I end today's lecture, I just want to share with you that I firmly believe that this technology actually has the potential to increase the contribution of renewable energy as an alternative to fossil fuel. I think that's all from me. Thank you.
Okay, thank you, Normaiza. Okay. So thank you for the very informative presentation. Okay, I would like to ask one question. Okay.
Yeah.
Just that before that, I think I have one suggestion. You did show us on the Grotthus mechanism explanation. That's good. It's just that maybe later, I think it's better if you can have some animation on the mechanism. It'd be much better for the non-technical people to understand it. Okay. All right. So my question is that you mentioned about lots about nephron membrane. Okay. So in a layman term, what is actually you can say about the nephron membrane? And does environment affect the nephron membrane properties? So that's
So sorry, the voice is kind of low. I cannot. Yeah.
Okay. First question, in a layman term, how are you going to explain about the nephron membrane?
How I'm going to explain on the nephron membrane?
Yes.
Okay.
And next is, does environment affect the nephron membrane properties?
Does environment affect the nephron membrane properties? So I'm so sorry, but can I get more explanation on the first question? I don't really understand it.
You mentioned a lot about the nephron membrane in a layman term, as to make it easy for other people to understand what is a nephron. How are you going to explain to people?
Okay. So for the first question, what is nephron, right? Nephron is actually just a separator, like a sieve. Okay, we just want certain molecules to pass it. So if we have a sieve, we want to separate, for example, rock and also a flower by using a sieve, and the sieve can always only sieve the flower, but not the rock, right? So actually membrane also work like that. We only need certain things to pass through it, but not other things. Okay, that is the first question. Secondly, on the second question, does environment affect the properties of the nephron membrane? Yes and no, actually. If we take good care of it, if we keep it, I mean, after using it, we keep it hydrated, then maybe the environment won't affect it that much. But if we keep it out there and let the high temperature of the room drying the nephron membrane, then we cannot use it anymore. I think that's it.
Okay. All right. So let us have one question from Engineer Nur Hisham.
Okay, Assalamualaikum, Normaiza.
Salam.
Okay, interesting topic on the renewable energy. Okay, my question actually is that how sustainable is this MFC process in terms of releasing of byproduct into the environment?
In terms of?
Releasing byproduct into the environment.
Oh, okay. So based on the knowledge that I have right now, since MFC, besides for bioelectricity production, it can also treat waste, right? So how the waste was treated by when the bacteria consuming the, how do I say it? Let's just take wastewater as an example, okay? So if we use wastewater in the MFC, the COD will be reduced. The microorganism will reduce the amount of COD. Okay, so by releasing this waste that we have used, that we have actually treated in the nephron membrane, it can actually affect the environment positively. Okay, because instead of releasing contaminated substrate that we have used previously in the MFC, we actually able to release treated waste. Am I answering the question right?
Okay, thank you.
Okay. One last question from Technology Skang.
Yeah, interesting because I remember about 2 years ago, I met the senior president of Petronas, and that was the first time I couldn't understand what was the biofuel cell, because in my lines, especially in cathode protection, we deal a lot with the anodes and to protect the cathode, and we always have open electrolytes so that the N ions and the cat ions can exchange freely. And now listen to your presentation that there's a filtration between the anodes and the cathode come about. Is another learning point for me to understand the battery more than just the exchange of the electrons and flow of the current. Now, about this naphthalene, I think that is the way that they pronounce naphthalene. Other than currently what you're working on naphthalene, are there any other alternative membranes that been developed or been developing that could possibly offer better cost effective and performance compared to naphthalene, and in that can go into the industrial scale for the microbial fuel cell system? So are there any development going on, or what are going parallel at this moment? Thank you.
Thank you for the question. So since MFC itself have not been used in industrial scale, right? So of course the membrane still in developing as well. So your question, is there any other alternative for nephron membrane, right? So as I shared previously just now, I have shared the earthen membrane, right? So this earthen membrane that was fabricated from the combination of clay, what is it again? And other material actually was reported to have better proton conductivity compared to the Nephene membrane. The proton conductivity able to outperform this Nephene membrane. But of course, since Nephene membrane is more established, there are still things that we have to improve with the earthen membrane. For example, the thickness. So Nephene membrane was built to be very thin-like, right? But the earthen membrane the fabrication of the earthen membrane is still too thick. If I'm not mistaken, the Nephene membrane thickness is only 0.1 mm, and the thickness of the earthen membrane is 6 mm or 60 mm. So this thickness actually can affect the proton transfer. So yeah, that is another alternative, but we still have to further optimize it in the future.
Okay,
Thank
all
you.
right. Thank you, Normaiza.
Okay.
Okay, I pass back the session to MC.
Thank you.
Normaiza, can you stop sharing your slides, please? All right, thank you. Oh, okay. All right, so let's thank Normaiza binti Nordin once again. And before we proceed to the remaining three presentations, we would like to take a short break and hope to see you all back at your screen by 10:30 a.m. All right. 10:30 a.m. Yeah. So that is in 23 minutes. All right. Welcome back, everyone. It's almost 10:30 a.m. and now we would like to call upon Jerome Liew from University Malaya. And he will be talking about Maxine, the future of fast charging battery. Jerome, are you here with us?
Yes.
All right. I will stop sharing so you can start sharing your slide.
All right.
All right, good luck.
On a road trip, your friend drives to the petrol station to fill up his car. In 5 minutes, he had a full tank and could travel 600 kilometers. You, being successful in life, own an electric vehicle. You drive to a charging station to charge your car. And after 1 hour, you're still waiting for your car to fully charge and can only travel half the distance of your friend. Ah, what a bummer. Hello and good day, ladies and gentlemen. I'm Jerome, and I wonder, what is your ideal electric car? I believe it should at least possess conveniences of an internal combustion engine vehicle, low downtime, and long travel distances. However, an ideal EV should start from the ground up, beginning with an ideal battery. So, let us talk about Maxine and our journey to pursue the ideal fast charging battery. Maxine is a class of 2D nanomaterial, the same as graphene, that is made from a top-down approach from its precursor called MaxPhase. MaxPhase consists of alternating layers of Mx and A, whereby the M is a transition metal element, the X a carbon or a nitrogen, and the A is usually a group 13 or 14 element, aluminium or silicon. So it consists of alternating layers of transition metal carbide or nitride and aluminium or silicon. To make Maxine, we have to remove the A layer of this MaxPhase in a process called etching. By removing the A layer from MaxPhase, what's left behind is Maxine. And by adding the suffix "ene" to MX, it spells out as MXENE. And that is how we come about with this name, Maxine. The scanning electron microscope here reveals the morphology of a MaxPhase, and we can observe a tightly packed bulky crystalline structure. And after etching the A layer, we can see prominent interlayer spacings between each Maxine nanosheet. And this is a structure very much sought after in 2D nanomaterials because we can probably tell that they have an exorbitant surface area to volume ratio. And the transition metal nature of this Maxine also endows it with amazing electrical and mechanical properties. Furthermore, the synthesis of Maxine also gives them a unique and tunable surface chemistry, which in turn bestows upon them an incredible processability. Maxines are highly hydrophilic, and they can form colloidally stable solutions in aqueous dispersion and in organic solvents. So, how do we make this wonder material called Maxine? There are a couple of approaches to making it, but they generally revolve around removing the A layer out of the MaxPhase. The first ever discovered Maxine was titanium carbide by two researchers in Drexel University in 2011. In the hope of fabricating better electrodes for lithium-ion batteries, they immersed titanium aluminum carbide MaxPhase in pure hydrofluoric acid. This hydrofluoric acid etches and exfoliates the MaxPhase, producing a black viscous substance that was subsequently dried and washed, forming the Maxine we know today. But hydrofluoric acid, as all of you know, is one of the nastiest chemicals one can ever come across in the synthesis. So naturally, researchers try to avoid using hydrofluoric acid and search for alternatives. The first ever alternative discovered was in situ HF in 2014. It is a mixture of fluoride salts and hydrochloric acid that forms hydrofluoric acid on site in situ as it reacts with the MaxPhase. This is an extremely easy and primitive method, and it's cheap to run, and it's feasible at room temperature. It all sounds too good to be true until you realize that they suffer from poor etching efficiency because these in situ HF produces hydrofluoric acid at a much lower concentration that is less harsh to the etchant. And this makes the exploitation Of more exotic MXenes, for example, vanadium, molybdenum, and niobium MXenes, much more difficult. And some of the salts have difficulty in dissolving in aqueous dispersion, the most prominently being lithium fluoride, exacerbating the already poor etching efficiency. And ultimately, hydrofluoric acid is the main etchant in this reaction. So it's not ideal if you want a totally and completely green MXene. 4 years later, in 2018, hydrothermal assisted etching was introduced using a conventional oven to make titanium carbide and niobium carbide in 2018. And this was performed using in situ HF. And fast forward 4 years, in 2022, Sunway University, Malaysia introduced microwave, firstly utilized in hydrothermal assisted etching to make titanium carbide using in situ HF as well. Both of these approaches completed exfoliation in less than 20 hours, which is a marked reduction compared to the conventional methods, which require 24 hours. Because in an enclosed chamber, as the temperature rises, the pressure increases as well. And this aids in the dissolution of fluoride salt in aqueous dispersion, enhancing the etching efficiency of weaker etchants. This enables us to explore other weaker etchants that are greener, such as fluorine-free etchants, and green solvents to explore other MXenes that are not previously possible to exploit as well. And this combination also hastens reaction, speeding up reaction, reducing the duration we need to make MXenes. And last year, deep eutectic solvents was first employed to make titanium carbide MXene. Deep eutectic solvent, or DES in short, is a mixture of organic solvents with a melting point lower than any individual element. They boast the benefit of being cheap, feasible at room temperature, biodegradable, and low toxicity. And the first pair of DES ever used to make MXene was urea and choline chloride, and they reached a melting point of as low as 12 degrees. Do you know what is this 12? It was the number of days it took for a complete exfoliation. This is totally unacceptable considering you can actually make MXenes in less than 24 hours. So to address this, to promote green synthesis of MXenes, we employed a solvothermal approach, a solvothermal assisted etching using DES, and we achieved a complete exfoliation in just 18 hours. This is a breakthrough for green MXenes. So let us now revise the timeline of MXene synthesis of how it has evolved from when it was first discovered. In 2011, pure hydrofluoric acid, very nasty, was first used to make MXene, and it produces this beautifully etched MXene. 3 years later, in situ HF was used, and we can all tell the effect of exfoliation is less than stellar. The layers are not as open, they are not as wide, and it also suffer poorer electrical conductivity. And then hydrothermal assisted etching and solvothermal assisted etching come along. These etchings are better approaches to make MXenes because they actually produce MXenes with better quality than the conventional ones. The MXene flakes are larger, they are of higher quality, they are less defective because these etchants are less harsh to the material as well. And these factors are paramount to the electrical chemical performance of these MXenes. And more importantly, they save time and are greener than these conventional methods. So after deciding the best course to make MXenes, we are going to incorporate it into our silicon anodes to improve its performance. But first and foremost, why silicon? What are we trying to replace here? The diagram here shows the anatomy of a battery. You have an anode and a cathode sandwiching an electrolyte. We are trying to replace the anode of a battery. Commercial batteries use graphite-based anodes, and graphite anodes has a maximum capacity of 372 milliamp hour per gram. Having said that, silicon anodes have a maximum capacity of almost 10 times that of graphite. So why are we not harvesting this potential? What is stopping us from using this? There's a reason to this, but we have to first learn about the formation of a solid electrolyte interface. When an electrode comes into contact with an electrolyte, during cycling, that is to say charging and discharging, they react with each other, forming an SCI layer. An SCI layer is paramount to keep the voltage of the cell stable and to keep further reactions from the electrode and electrolyte. It keeps it stable. The problem of silicon lies in its massive volumetric changes during charging and discharging. When a silicon anode is charged, it expands in size and volume up to 300%, resulting in the formation of a huge SCL layer. And when it discharges, it shrinks back to its original size, and the SCL layer ruptures and gets destroyed. Subsequently, so you have lost the protection you just formed between the electrode and the electrolyte. So you're vulnerable to the formation of a new one, which is what happens when it expands again. When it is charged again, it forms a new SCL layer that is subsequently destroyed. And when you repeat this cycle many times, eventually you will get a thick and dysfunctional SCL layer that increases the internal resistance of the cell and causes great performance degradation. Now, what do these translate to in real life? It means a very swollen and a very hot battery. These are not ideal. So we've designed a strategy to construct a composite silicon anode with dual MXene protection. This construction consists of two assembly methods. Firstly, we'll mechanically mix silicon nanoparticles and MXenes together to form a layer-by-layer structure, whereby the silicon nanoparticles are intercalated between those MXene nanosheets. And then the structure will react with MXenes again in a hydrothermal setup and freeze-dried afterward to form a porous and three-dimensional MXene matrix. The former structure confines silicon nanoparticles from overexpanding and buffers their volume expansion, protecting the anodes from rupturing, whereas the latter can reduce the migration path of lithium ions and facilitate the movement of ions in and out of the electrode, resulting in an improved charging rate. In real life, your battery will no longer get swollen after a few years of usage, and it won't get hot after a fast charging session. With the implementation of this technology, batteries will definitely have reduced costs because silicon anodes have such a big capacity. You only need a less material of it to make batteries of the same capacity or even better compared to graphite anodes. And with lesser material used, battery packs will also have lesser mass. They will have lighter weight, which makes the electrification of commercial vehicles like trucks, lorries, etc. much more feasible. Thirdly, the use of these high-capacity silicon anodes increases the range of EVs immensely, up to 700, 800, 900 kilometers, compared to the 500 kilometers the most advanced electric vehicle can offer you in this day and age. And MXene also supports fast charging. The implementation of MXenes into electrodes will enable batteries to handle fast charging more feasibly, and it can support up to 10C rate of charging. That is to say, you can now fully charge your car in under 10 minutes compared to the hours upon hours you would have to wait at a normal charging network. Our research team strives to make innovations and to seek improvement in the field of energy storage devices and harvesting devices. We're working on batteries, supercapacitors, superbatteries, and solar cells, just name a few. And we have also taken part in lots of exhibitions, with the most recent ones being ITEX in 2023 and 2024. And we won a gold award and a special climate award for the use of these devices and materials. And MXene was one of the exhibits as a nanomaterial and as an electrode material in batteries. This July this year, I was also offered a scholarship by the Green Sciences for Sustainable Development Foundation to attend classes in Green Chemistry Summer School in Venice, Italy. And there I posted about the evolution of MXene synthesis, how it evolved from 2011 and what it is today. And our team is also co-funded by the Erasmus Plus program of the European Union. So next time you go on a road trip with your friend, not only you can go as far as you can also charge your car as quickly as he fills his car. Thank you.
Okay, thank you, Jerome.
Okay.
Okay. So thank you for such an insightful presentation and congratulations on your successful journey with MZin. Okay. All right. So we're going to start with the Q&A session. So I'm going to call first Professor Mariam, please.
Right. Thank you, Dr. Nisa. Well done, Jerome. Okay, I
Okay,
actually
thank you.
enjoyed what you, even though I joined in quite late, but I think I really enjoy your slides and everything, okay? The way you deliver. Right. I only have one question.
Mhm.
How does the performance of this Maxine-based composite anode compare to other anode materials?
Okay, we can compare Maxines to some of its nearest competitor. Maxine is a
Yeah.
2D nanomaterial, right? So we compare it to graphene. Now, when you compare these back to back, Maxines has many benefits. First and foremost, it's hydrophilic, so it can form stable dispersions very easily compared to graphene. The graphene, they don't form dispersions in solutions, aqueous solutions at all. And Maxines also have higher conductivity than graphene. So when it comes to composite anodes with these materials, Maxines are almost always preferred. And it does deliver higher conductivity and higher capacity compared to graphene-based materials, anodes with graphene as an additive material in their electrodes. It is better in many ways. Yes.
All right.
Okay, all right.
Thank you.
Okay, thank you, Professor Mariam. Okay, so next one question from Engineer Norisha.
Okay, thank you. Hi, Jerome.
Hello.
Interesting topic that you're presenting. I think with the current popularity of EV, I think the main issue actually people are talking about the sustainability of the batteries. Okay, so based on the Maxine process, I want to actually know how sustainable is this process in terms of releasing any toxic gases into the environment.
Toxic gases usually comes from the use of liquid electrolyte, but when it comes to Maxine, it doesn't actually when it comes to these composite anode, it doesn't release any toxic gases in the environment because most of the gases comes from the electrolyte, the liquid electrolyte, and that is something we also try to replace with solid state electrolytes, right? But when it comes to sustainability, Maxines enables us, okay, in the battery, in a conventional battery, in a graphite anode, say, you have the active material, you have some other binders, and these are not conductive. And this actually disrupts how easy it is to recycle these things. But with Maxine, if you use Maxine in a composite anode, you can negate the use of these things. So you don't have to use binder, you don't have to use some of the non-conductive binders in your electrode. So it's definitely much more sustainable compared to graphite anodes. And like I said, silicon anodes, they have such a massive capacity. So it's much more sustainable than the conventional ones because you don't need that much material to get the performance you need, to get the performance you desire. So that's on the sustainability standpoint when comparing to conventional ones, commercial ones, to this material.
Okay, thank you.
Okay, all right. Thank you, Engineer Hisham. Okay, so I have one last question, yeah. So how about in terms of cost, the biodegradability, the toxicity of this Maxine?
Maxine, thank you for the question. Maxine is in an anode, you can easily reuse it. You can easily, in a composite anode, you can easily reuse the Maxine in the anode because when it comes to commercial ones, it's difficult to recycle it. But when it comes to Maxine, you can actually reuse the Maxine in the composite anode and make it something else. For example, you can have the anode, which has its life cycle ended. That means it's no longer useful as a battery. You can make something else out of it. For example, titanium dioxide, which is used in paints for white paints, can be used as a catalyst. And this can be done by just oxidizing the Maxines in the material. And by oxidizing it, you get this titanium dioxide, which can be used for many other functions as well. And yeah, it's completely recyclable, it's reusable, and you can even make second life electrodes out of these Maxines, which can perform not as good as the first batch, but the performance is still significant as a battery. Thank you.
Okay, thank you for the explanation, Jerome. Okay, all right. So pass back to the MC.
All right. Thank you, Jerome. Thank you to the judges. And now we will proceed to our fourth presentation for the day. We have with us Ainaa Amirah, binti Marzuki, alias Hadi. She is a PhD student, and her topic will be Materials Then and Now, exploring the potential of magnetorheological foam. Ainaa Amirah, are you here?
Yes, I'm here. Can you hear my voice?
Yes. I will stop sharing so you can share your slides now.
Mhm.
All right. We see your slide. There are some black boxes.
Yeah, yes.
On the right, yeah.
Let me just adjust.
All right.
Okay, I hope it is clear now.
Yes, all good. All right, good luck.
Ladies and gentlemen, let's take a moment to appreciate our hands, our fingers. Think about how your hand works in daily life. You effortlessly adjust your grips based on what you're holding, whether it is a fragile piece of fruit or a heavy tool. You can switch between being gentle and applying strength without a second thought. Now, imagine if your hand could only exert one type of force. You would crush delicate objects or be unable to lift a heavy ones. Life would be far less efficient. This is exactly the challenge that robotic grippers face. Unlike human hands, most of the grippers have fixed properties, either soft and gentle or strong and rigid. This lack of flexibility limits their ability to handle a variety of tasks in a real-world environment. What if robotic grippers could be adaptive, just like your hand, provided by a material that could be soft when needed and strong when required? How is this possible? Stay tuned to find out. Assalamualaikum and a very good morning to all. My name is Ainaa Amirah Marzuki from University Technology Malaysia. Today, I'm excited to bring all of you for a journey on the development of our material through my presentation entitled Magnetorheological Foam, a Revolution in Tunable Material, transforming from soft to rigid in an instant. Here is how I'm going to proceed with this lecture. First is on the introduction. I would like to introduce to you what is robotic gripper and what exactly is magnetorheological foam that will make this gripper adaptive. Next is on the background of material, where I will be elaborating and addressing all the reasons on choosing the material's composition. After that, I would like to highlight on the fabrication process, because in developing a material, the process itself holds a significant impact that influences the final properties of the material. This lecture will also include a short discussion on the material's characterization, which relates back with the potential use for the gripper. And lastly, a conclusion on the overall lecture. Let's get started with the introduction. You must be familiar with the word robotics, but what is robotic gripper? It is a mechanical device that allows to pick up, hold, and move objects. They are commonly used in automation or manufacturing, basically to handle tasks from assembling products to sorting items. Nowadays, along with the evolution of technology, robotic grippers can even be found in healthcare as they assist in surgeries and handle medical tools safely. In short, robotic grippers make tasks easier and more efficient by improving speed, accuracy, and flexibility in many areas in our life. Current grippers use different materials based on the task, such as metal for strength, while rubber or silicone for gentle handling. However, the fixed properties of this material create a distinct gap between the strength and gentleness, limiting versatility and making the system more complex because each different task might need different type of gripper. This is where magnetorheological foam comes into play as another alternative of potential material for the robotic grippers to overcome this problem. What is magnetorheological foam? Magnetorheological foam, which is also known as MR foam, is a type of smart material, as written in the word magnetorheological. Magneto refers to the magnet, while rheology refers to the study on the response of material. Therefore, magnetorheology means that this material has the ability to give response upon the presence of magnetic field, as shown in this clip. As a result, the properties of this material can be continuously controlled, rapidly and reversibly changed by the manipulation of external magnetic field strength. As you can see in my hand, this is the fabricated MR foam sample. It has a porous structure, giving it the advantage of being lightweight, at the same time having high flexibility and durability. Since the properties of this material can be tuned in a real-time situation based on the applied magnetic field strength, MR foam stands out as a versatile material that is suitable for applications requiring dynamic response. What is the content of MR foam that make them to have this ability? MR foam commonly made up from two components, which are the matrix and magnetic particles. Normally, MR foam uses polyurethane as the matrix. As we know, PU foam has been widely commercialized as it is a versatile material that can be prepared in a very simple fabrication process. With only two chemicals named polyol and isocyanate, you can already fabricate a PU foam. In fact, the properties of PU foam can be adjusted based on your requirements by just regulating the ratio of these two chemicals. While to make MR foam magnetically responsive, a type of soft magnetic particles such as carbonyl ion particles are being utilized. Soft magnetic particles are chosen for MR foam because they have the ability to give response in a very fast way. Based on the magnetic properties observed by a vibrating sample magnetometer as shown in this graph, this particle has a very narrow hysteresis loop, which means when magnetic field is applied, it has a fast response to magnetize, and when we remove the magnetic field, it demagnetizes quickly. Soft magnetic particles also have high magnetic saturation properties, which means they can achieve a strong magnetization even under a low magnetic field. Moving on to the next part. As mentioned earlier, to produce material, especially porous material, the fabrication process plays a significant role in producing material with great properties. This is because it is all interrelated. Process will influence the structure, and the form structure will give influence to the final properties of the material. There are three key points we take into account in producing MR foam. First is the flexibility of matrix. Next is the amount of magnetic particles to ensure optimum response to the magnetic field. And the third one is the structure of the foam to ensure longer endurance of the material. This mixture of PU and magnetic particles typically undergoes two types of forming process, either a free forming process or a constrained forming process. The foam was set to rise freely in a free forming condition, while it is the opposite for the constrained forming condition. The foam was set into a closed mold setup, and for this reason, the foam rises in a restricted environment. It is an advantage for us if we fabricate using a constrained forming condition because we are able to control the density of the foam according to the desired needs based on the volume of the mold. Now, among various characterization processes available, there are two characterizations that are typically carried out for MR foam. First is the morphological analysis. It can be conducted using a scanning electron microscope or even a digital optical microscope.
Based on a micrograph obtained by an optical microscope as shown here, MR foam fabricated with constrained forming process, which is the micrograph on the right, has better structural properties with smaller size of pores as compared to the one fabricated by free forming process as shown in the micrograph on the left. This is mainly because of the restriction created during the constrained forming, trapping more air required by the forming process, and with the presence of magnetic particles, it will contribute more energy for the forming took place. This will trigger the formation of pores, resulting to a larger number of smaller size of pores to be produced. To imagine this, let me give you a simpler situation to relate with this formation of pores. Imagine if you are playing with the water bubble. If you blow it like this puppy, slowly and steadily, you will create a larger size of bubble, right? But when you blow it with a higher energy like this little girl, smaller bubbles will be produced. Same situation happened for this formation of pores. Constrained forming condition and the presence of magnetic particles will create more energy due to a more frequent collision between the magnetic particles. And for this reason, smaller size of pores will be produced. The second characterization is rheological analysis. When magnetic field is applied to MR foam, the pores tend to elongate as the result of the reaction of the magnetic particles towards the magnetic field. These changes can be analyzed using a rheometer, where it is commonly conducted under the presence of magnetic field. It is important to conduct this analysis because the behavior of MR foam varies depending on the strength of the magnetic field. From this analysis, we can observe that the higher magnetic field we apply, the higher storage modulus we could achieve. Or in other words, higher storage modulus represents that this material to become more stiffer. As shown in this clip, without the magnetic field applied, MR foam has high flexibility, where it translates that this material is soft. But with the presence of magnet, as shown in this clip on the right, it becomes stiffer by bending towards the magnet. To relate back with our potential application just now, this dynamic behavior of MR foam allows a real-time tunable properties where if we require gentle grips, for example, to pick up an egg, like how gentle I hold this egg, you can just tune the magnetic field strength low. But if you require stronger grips, as shown in this clip, or maybe like how I grip this bottle, you can just tune the magnetic field strength higher. Interesting, right? This unique characteristics of MR foam shows that it can be a promising candidate for applications that require dynamic behavior. In conclusion, we can say that with this ability to transform material from a passive to a dynamically adjust its properties in a real-time situation, MR foam opens a new possibilities for innovation and provide efficiency across various industries. MR foam also might have the potential to reduce the cost of our existing conventional material because just imagine, with a thickness as thin as 1 millimeter, you could achieve properties as great as current material have. And with magnetorheological foam, you can even get an adjustable properties just like the behavior of your hands. Next time, when you look at your hand, gripping items like a bottle, you remember this lecture and you will remember magnetorheological foam. Thank you for your kind attention for this lecture.
Okay, thank you, Ainaa Amirah. Okay, thank you for such a good presentation. Okay, so now we proceed with the Q&A. So, Professor Mariam, please, one question.
Yes, hold on. Okay, thank you very much, Ainaa. I really enjoy what you presented just now about this MR foam. I just want to know, how does this MR foam compare to other smart materials or other technologies being developed for robotic grippers?
Okay, Thank you so much for the question. So what is the difference between MR foam and other smart material? So the difference is actually on the implementation of the reaction towards the magnetic field. So our material will react smartly according to the strength of the magnetic field. So that is my answer. Thank you.
Okay, so am I allowed to have another question? Is it okay? One more, it's just related to that.
You may ask another one question.
Thank you very much. I just want to know about this. How do you think the production of this MR foam can be made more sustainable?
Okay. From my opinion, how can MR foam contribute to the sustainability is that with MR foam, the duration or the lifespan of this material can be longer compared to the existing conventional material. Why do I say that? Because even if the strength of the material reduced over the time, we can still input a slightly stronger magnetic field towards the material, and it will become, it will give the same strength as you require. So the longer lifespan will contribute towards the sustainability, as we do not have to replace this material as frequent as conventional material. So that is my opinion on the contribution towards the sustainability. Thank you.
Thank you.
Okay, thank you, Professor Mariam. Okay, next, one question from Technology Skang.
Yeah, after Professor Mariam asked 2 questions, I tempted to ask more questions too, but I will remain to one. I often watch the video came across in news and where the robotic arm was moving, taking the car doors in the automobile assembly plants, thing like that. Then flipped my mind recently that more of robotic has made into more human look kind of robots, and to a certain extent it was a fake robot that which more of the human than the real robots. Now your presentation and your research is really interesting, and looking into the magnetic compound that that can change the stiffness. Now, I have a technical question in mind that now with your foam compound, which is already fixed, what were there behind that the magnetic field could be controlled with the real time? Because in my understanding, the foam composition should be already fixed. Now, in what way the mechanism came about that the properties, the rigidness, they can be tuned from there? Could you explain a little bit behind that?
Okay. Okay, thank you for the question. May I just repeat your question to make sure I understand about your question? So you are wondering on how is the mechanism behind the rigidity or the change of rigidity of this MR foam upon the real-time situation. Am I right?
Yeah. Yes.
Okay. So the real-time situation is reflecting on the input we put towards the material. So when the magnetic field is applied to MR foam, the MR foam is magnetized, and the particles inside the MR foam actually it tends to align towards the direction of magnetic particles, and due to their magnetic properties, they're attracted towards each other. So this will form a chain-like structure, and because of this formation of chain-like structure, it will create a reinforcing network within the foam structure based on the strength of the magnetic field. So the foam, which is typically soft without the magnetic field, is now have a strong internal structure due to the chain-like structures formed that can resist deformation. So I think that is the mechanism behind the rigidity of MR foam. Thank you.
Thank you.
Okay, thank you, Technology Kang. All right, one question from me. Okay, so what are the challenges that you face? Okay, during the fabrication process of this MR foam.
Okay, thank you so much for the question. The challenges faced throughout my research is that I observed this material as for now with the current composition used. I realized that this material has a saturation point in which the MR foam only will give response up until 0.6 Tesla, in which beyond this magnetic field strength, the properties slowly show a saturation behavior. So the stiffness of MR foam will not change above this magnetic field. So this leads to the challenge to make sure the strength, the stiffness of MR foam is enough for the use for the robotic grippers example. So to overcome this, we actually tried to produce another procedure by using different composition, such as by varying the concentration of magnetic particles. And we actually observe the enhancement behind the effort we put. So this is the experience, the challenge I faced throughout my research. Thank you.
Okay, all right. Thank you, Ainaa Amirah. Okay, so pass back to the MC.
All right, thank you so much, Ainaa Amirah. Now we will proceed to our final presentation from University Technical Malaysia, Malacca. We have Aslam Hadi bin Hamzah, a master's student, on the topic investigation of recycled PET based on mechanical properties through fused deposition modeling, FDM process. Aslam Hadi, are you here with us?
Yes, I'm here. Can you
All
hear me?
right. Yeah, I see you. I hear you. Can you try to share your slides?
Right.
All right.
Is it clear on the slide?
Yes.
Assalamualaikum and a very good morning to the honorable judges, audience, and participants that are here today. I hope you guys have a good breakfast because I need the energy to guys hearing my lecture regarding the investigation of recycled PET based on the mechanical properties through FDM process. My name is Aslam Hadi bin Hamzah, currently a master's student here at UTM, and this is my lecture. So before we dive in onto what my research is about, I want to give a quick view regarding my research. So in 3D printing applications, various printing parameter is crucial to achieve the optimal mechanical performance for 3D printed parts. Therefore, this research aims to investigate the effect of varying wall line count on the mechanical properties of recyclable polyethylene terephthalate blended with high-density polyethylene through the fused deposition modeling method. The blended material of 1% rPET and 99% HDPE was used as a filament for the FDM process with a varying wall line count of 6, 18, and 30 layers. The 3D printed sample were mechanical properties tests and also thermal analysis were evaluated. Experimental results shows that the 30 layers of wall line count produce the highest value in tensile strength due to less porosity. It also shows that the tensile strength of blended rPET is 2% compared to the PLA material. Differential scanning calorimetry analysis show that the blended rPET exhibits low melting point compared to PLA. So before we start, I want to ask all the audience, what do you guys know about 3D printing? Is it something very common or uncommon here in Malaysia? So even some of you may know, I insist to explain to you what is 3D printing. So 3D printing or additive manufacturing process is a process to create 3D printed parts layer by layer. There are many types of 3D printing techniques. The most common one is fused deposition modeling. It uses plastic filament such as PLA or TPU to create 3D printed parts. Other than plastic filament, we also use resin to create 3D printed parts. A UV light will harden the resin and the end will create the 3D printed part. And lastly, is use plastic powder such as in selective laser sintering. However, common technology nowadays have advanced using metal powder to create a stronger 3D printed part by using aluminium or titanium for medical purposes. However, there are few issues regarding with 3D printing techniques. So the most common one is the material itself. So the material itself is recyclable bottle. Without the recycling of this plastic bottle, it can create a hazardous waste, a danger to the environment, health, and economy. Therefore, we need to recycle this bottle to protect the natural resources. Furthermore, printing parameters in the FDM process can also affect the mechanical properties of 3D printed parts. So within these two, what is the common thing that I want to say is, so the first step is by recycling this plastic bottle, we can create a new 3D printing filament using extrusion process for FDM method. In addition, there are many types of printing parameters that can affect mechanical properties such as infill density, layer height, printing temperature that have shown in recent literature works. However, the printing parameter of wall line count has shown lacking in the 3D printing area. Therefore, an investigation of varying wall line count is conducted for the FDM process. So the first objective of my research is to develop 3D printed sample using recycled PET material with varying wall line count through FDM method. Number two is to evaluate the characterization, observation, and mechanical properties of blended rPET material. And lastly is to compare both material in terms of mechanical characteristics and thermal analysis. So the scope of my research is to blend the rPET material with HDPE to create the 3D printing filament. We then proceed to the 3D printed sample with varying wall line counts of 6, 18, and 30 layers. The 3D printed sample proceed to the mechanical property test and also microstructure observation, and also thermal analysis is conducted. So below shows the process work consists of mechanical properties, morphology, and thermal analysis. So the first step, we prepare the raw material of the blended rPET. After we prepare the material, we proceed to the development of 3D printing filament with the use of the blended rPET. After the development of the 3D printing filament, we proceeded to 3D printed the sample with varying wall line counts. And lastly, evaluation and characterization observation were conducted, also mechanical property tests. So here shows the development on how the 3D printing filament is developed. So the first step, we prepare the raw material preparation. That is the plastic bottle or recyclable polyethylene terephthalate. So these plastic bottles were collected around the UTM area, mostly in cafeterias and also offices. These plastic bottles were cleaned thoroughly and cut into smaller strips for the crushing process. So the crushing process will create the rPET material into smaller pieces for easier extrusion process. So after the crushing process, we manually mix the rPET and the HDPE into a blender of 1% rPET and 99% HDPE. We then proceed to dry the blended rPET into the oven to eliminate any moisture within the material. So after the drying process, we proceed to the extrusion process to create the 3D printing filament for FDM material. And lastly, the filament itself will be used in the FDM 3D printing process. So after the 3D printed process of the sample with varying one line count of 6, 18, and 30 layers, we proceed to the mechanical test consisting of tensile test, impact test, and density test. And we proceeded to the material characterization using field emission scanning, electron microscopy, and also thermal analysis of the differential scanning calorimetry analysis. So here's the experimental result showing the tensile strength of the blended rPET. As you can see on the bar chart on your left, shows that the blended rPET is increasing in tensile strength with increasing one line count. This also shows that the blended rPET is comparable with PLA in terms of tensile strength. These FEM images also shows that with increasing one line count can reduce the voids and porosity within the sample, supporting the tensile data. So here shows the density level within the sample regarding with the blended rPET. It shows that the blended rPET is also comparable with LA, and the SAM images also support the density value with increasing one line count. However, for the impact strength, shows that the 18 layer one line count is much more higher in impact strength compared to the 6 and 30 layers. This is due to the 80 layer have much better cohesion when doing 3D printing process. So below shows the result of the differential scanning calorimetry analysis. Below shows the result of the blended rPET exhibits a lower melting point compared to the PLA. With the lower melting point, we can use for 3D printing applications much more easier and much more faster. So with the current research, I have successfully created a prototype regarding with my innovation. This innovation is used for 3D scanning process. So for my innovation, we are currently right now at technology readiness level of level 6, a viability demonstration. This product has been within the industry and field tested will be conducted with 3D scanning applications. So there's a video showing on how the product works. So on the left side is the video without the use of this product, and the right side is the video with the use of our product. For 3D scanning process, if you want to scan the part itself, we need to place these markers. Same like the video on the left side. However, it is very tedious. So with the use of this product, we don't need to place these markers. We just need to place this product near to the part that need to be scanned. So regarding with the product, we have a technology transfer with 3D Gen Sedia Berhad, a 3D printing company in Shah Alam. We have also done a technology transfer with Glassware Sedia Berhad regarding with the product. So for the product, it's very aligned according to the forecast with the recycling of plastic bottle and 3D scanning market increasingly every year. Our potential market is also through automotive and other commercial sectors. So the conclusion that I can make from this research project is that we have successfully developed the 3D printing filament of 1% rPET and 99% HDPE for FDM process. Number 2 is that the best one line count for the FDM process is the 30 layers one line count based on the experimental result on the mechanical and thermal analysis. And lastly, the mechanical properties of blended rPET is comparable between 2% until 30% compared to the PLA material. So regarding with my product, I have also successfully registered and intellectual properties regarding it. And I have also won a few innovation competitions in IRITEC, Jejak Inovasi, and also in Finale Week regarding with my product. I have also submitted 2 journal papers for publication in Scopus Index regarding with my research. So that's all from me. I want to give thanks to University Malaya to organizing this competition, and I hope I can join other competitions organizing by itself in the near future. Thank you.
Okay, thank you, Aslam Hadi, for such a good presentation, and also congratulations on your journey with your research project. Okay, all right. So now I'm going to call Professor Mariam, please. One question.
Yes, thank you very much. Aslam, Mr. Aslam. Okay, good.
Yes.
I really enjoy your presentation just now. Okay, given the success of using this RPET blends in the 3D printing, do you think that this 3D printed RPET parts be further modified or treated to improve their mechanical properties or other characteristics? What do you think?
In my opinion, based on literature works and also journal papers that I have read, there's a few ways to improve the mechanical properties itself. First, in my research, I have only using 2 materials to blend the 3D printing filament. First is the rPET and HDPE. But based on my literature works that I have read and journals, they also have mixed with filler, such as like what they call filler, like aluminium, like smaller, like other plastics, other polymer that can improve the rPET itself. So in my opinion, if there's a way to improve the blend of rPET and HDPE, so there must be ways to improve it in the near future for mechanical purposes. So that's my opinion.
Okay, thank you.
Okay, all right. Thank you, Professor Mariam. Okay, next, one question from Engineer Norisham.
Okay, thank you. Assalamualaikum, Aslam.
Waalaikumsalam.
Okay, basically, quite interesting topic, especially we are looking from waste to wealth. So this, I think, where you are looking at sustainability is concerned, how to actually recycle product and generate wealth from it. Okay? Based on the process that you are actually presenting on the mixture of 1% rPET with 99% HDPE, normal practice at the end of the life cycle, okay, to segregate this material or to recycle this material will actually be more higher because of different recycling method. Okay, so my question here actually is that why do you not consider 100% HDPE?
Okay, the reason why we don't use 100 HDPE, the first reason is I have tried to increase the rPET to 20 or 25%. But with the increase of rPET, I can see that when doing the extrusion process, the filament is not successfully. The end product that the filament will be liquid and cannot be solid. So the reason why I don't use 100% HDPE is my aim is to use the plastic bottle as a recyclable bottle. So there's also a legislation showing that the PET bottles in the near future by 2025, at least 25% of recycled plastics needs to be contained in plastic bottle. So the reason that's the reason that I don't use 100% HDPE, because the main reason is we want to recycle this plastic bottle to be to be in a connection with the recycling committee throughout the world. So we play a part to recycle this plastic bottle. So that's why I don't use 100% HDPE, is that to recycle this plastic bottle to a better future.
Okay, thank you.
Okay, all right. One last question from Technology Skang.
Yeah, interesting, Aslam. Especially I see that your research work has pretty much industry ready with your signing and cooperation with some of the companies, one of the companies in Shah Alam. Now, back to more industrial related question that I have in mind is that are there any like production and the skill ability challenges that industry should be aware of when integrating your rpad based materials into a larger scale 3D printing processes? So what are the challenges the industry should be aware of in your work here?
In my opinion, the challenges if the companies throughout Malaysia use the material based on my research works. So these the challenges are in terms of mostly the printing parameters itself. So what is the temperature that is the best for the recyclable of the blended rPad? What is the strength? What do you want? What the mechanical properties that you aim for? So probably to extend into a larger company, that's the parameters. The printing parameters is crucial for developing a larger scale in the 3D printing company. So other than that, I guess it's only the printing parameter. Probably the potential for marketability is also an issue due to the product is only used for 3D scanning process. So that's all based on my opinion.
Thank you.
Okay, thank you, Aslam. Okay, that's all. All right, I pass back the session to MC.
Thank you, judges, and thank you, Aslam. So we're done with all of our presentations right now, and we are awaiting the jury's deliberation. So please give our jury some time to decide on the best presentations of the day. And the judges will take this time, while the judges are deliberating, please take this time to relax as we await the results. And please come back to your screens at 12:15 p.m. That is in 45 minutes. Yeah. All right. Thank you, everyone, for your time and patience. See you back in a few minutes. Welcome back, everybody. We have reached the final section of our event today. And I hope you've all had a good lunch because soon we will be announcing the winners. But before that, we would like to invite Senior Technologist Nur Hisham Yahya, Deputy President of Institute of Materials Malaysia, to give a closing remark.
Okay, thank you, Ms. MC. Assalamualaikum and very good afternoon to everyone. It fills me with great pleasure to extend warm welcome to all the distinguished guests, judges, and participants of the Material Lecture Competition 2024. In short, MLC 2024. The MLC competition, an initiative of Institute of Materials Malaysia, aims to provide a platform for young students and researchers below the age of 28, especially in the field of material science, technology, and engineering, to showcase their capabilities and share their knowledge on materials and their role in society. This event has become an esteemed and trademark annual occasion in IMM's calendar, and it is an honor and privilege for IMM, the Institute of Materials, Minerals and Mining, IOM3 in the UK, and University Malaya, to co-organize this significant competition. At IMM, we not only provide career advancement opportunities through technical competency, certification, and education training courses, but we also dedicate to empowering and engaging with young materials scientists and engineers. Our goal is to foster enduring relationship with the community, society, and our nation. I encourage all members of academia, industries, and students to actively contribute to promoting the importance of materials in Malaysia by joining IMM and playing a pivotal role in its activities. We are deeply grateful to IOM3 for their continuous support and to University Malaya for successfully hosting and co-organizing this year's event on a virtual platform. My heartfelt appreciation and congratulations to the MLC 2024 Organizing Committee, expertly led by the Organizing Committee Chairperson, Dr. Muhammad Khairi Faiz, and all those involved in making this online lecture competition a resounding success during both the semi-final and final round. I would also like to express my gratitude to all the competition judges who graciously accepted our invitation despite their busy schedule. To Dr. Abdul Hakim Yusuf of UTM, Chairperson of the MLC Committee, and to all the MLC Committee members and university representatives for their dedication and commitment in organizing not only this final but also the internal competition in their respective institution. To select the winners who had the privilege of participating in the MLC 2024 semi-final held on 3rd September 2024. Congratulations to all the MLC 2024 semi-final participants from 13 public and private universities in Malaysia for their unwavering commitment to the competition and to the top 5 contestants who qualified for the MLC 2024 final today. I wish all the best to the first place winner of the MLC 2024 final who will represent Malaysia at the Young Persons World Lecture Competition 2024. Let us embrace the spirit of innovation and knowledge sharing as we witness the remarkable representation of this young talent. I'm confident that the future of material science and engineering in Malaysia is in a capable hand, and I eagerly anticipate witnessing the exceptional contribution that will emerge from this event. I wish all a great event. Thank you.
Thank you, Senior Technologist Nur Hisham Yahya. That was a very insightful speech. And now we are going to the moment that we've all been waiting for. It is now time to announce the winners of the National MLC 2024. And for this, I would like to invite Dr. Muhammad Khairi Faiz, our chairperson, to announce the winners.
All right, okay. Thank you for your patience, everyone. What a fantastic series of presentations that we've had today. Each of our finalists has demonstrated remarkable knowledge, passion, and also dedication, making these competitions one that has truly showcased the talent and also potential in the field of material science and engineering. So before we announce the results, I would like to take a moment, all right, to thank our esteemed judges for their time, expertise, and also thoughtful evaluation of each presentation. And also, I would like to congratulate all of our finalists. Reaching this stage is already a tremendous achievement, and your hard work and innovative ideas are really commendable. Every one of you should be incredibly proud of yourself. You have all made these tough decisions. All right, okay. And now, the moment that we have all been waiting for. The third winner, all right? The third winner of the Materials Lecture Competition 2024, who will be receiving 1,000 ringgit Malaysia is Aslam Hadi Hamzah from University Technical Malaysia, Melaka. Congratulations. Next, the second winner of the Materials Lecture Competition 2024, who will be receiving 2,000 ringgit Malaysia is Ainaa Amirah binti Marzuki from University Technology Malaysia. Congratulations. And last but not least, the first winner of the Materials Lecture Competition, who will be receiving 3,000 ringgit Malaysia and also representing Malaysia to Young Person World Lecture Competitions 2024 is Jerome Liew from engineering.unimalaya. All right, congratulations again. So all of you have earned this through your dedication and also outstanding presentation. All our winners here, we are excited to see how you will continue to contribute to the fields of material science and inspire the future scientists and researchers. Once again, congratulations to all of our participants from the semi-final up to the finals round, and also for our winners today. We look forward to seeing all of you in the next sessions. And thank you everyone for being here and supporting these incredible individuals. Thank you. Back to MC.
All right. Thank you, Dr. Muhammad Khairi Faiz. You said all there is to say, and now we want our top 3 winners and our judges to please turn on their cameras so we can take a virtual group photo together one last time. All right, we have everybody here. Okay. All right, everybody is free to join this group photo. So please turn on your cameras if you are present in the meeting. All right. If we're ready, 1, 2, 3, smile. One more. 1, 2, 3, smile. All right. Thank you, everybody. So this concludes our event. Hopefully, everybody has learned something from the top minds of Malaysia, especially in the field of the materials. And with that, we would like to conclude our event. Hope to see you next time on the international grounds. And thank you very much, everybody. Wishing you very good luck in your future. All right, thank you.
Thank you and congratulations.
And congratulations
Okay,
to
thank
all the
you.
winners.
Congrats to the winner and all the best to Jerome.
Thank you. Thank you.
Back to you all. Okay, thank you. Congratulations to the winner. Okay.
Thank you, Dada Kim. Thank you very much.
Yeah, thank you very much also to Center of Advanced Material UM for hosting this successful event. Okay.
By the way,
To
Dr.
Faiz and
Faiz,
also including
who will be the host next year?
we haven't decided yet. Maybe on
yeah,
could be tak tahu lagi siapa. Okay. Yeah. Hopefully that we can repeat this successful punya event for next year's. Okay. So congratulations to what we call Jerome Liew.
Thank you very much. Yeah.
For the best for the international level. Thank you.
Okay.
Yeah, Mr. Faiz and MLC committees, and also including the what we call it IMM committees, okay, who work tirelessly in order to make sure that this event running smoothly. Okay. Okay. Thank you very much, Dr. Faiz. So until we meet again, okay.
Okay. Thank you very much, Dr.
For the next time. Yeah.
All right. Okay.
Okay, and so please send my regards to Professor Rafiq.
Oh, Prof. Rafiq.
Yeah,
UTM.
Basically, he is my PhD supervisor here.